So at this point, let me introduce Eduardo Valle, one of our top scoring participants, to give a talk about our approach.
Thank you very much. Good afternoon. So let me start by presenting the team. This is our current team, and the context of this picture was a little piece that the university did for our website when the challenge results got out. we were very, very happy about the results. So let me talk a little bit also about the team history. We have been working with melanoma screening, the classification of melanoma, since 2014. This is our first paper. This is a paper that we published in the Brazilian conference, ISBI, at the time using bags of words for the classification task. And around that time, we had two master's theses defended on the subject, the thesis of Michel and the thesis of Michael. Yes, there is a running joke about their names. So Michel's working with the bags of words features, and Michael's working at the time with deep learning, with transfer learning for several tasks, one of them melanoma screening. And at the time, we had invested a lot of energy and research time in the bag of words model. And we were kind of hoping against hope that in the context of small-scale medical images, the bag of words model would still be competitive with deep learning. But so Michel used the best available bags of words at the time, and Michael used very, very summary basic, really the simplest deep learning techniques, and the deep learning still won. So this was, at this time, we realized that there was no competition possible with the deep learning. Later this year, in 2016, we had this report published. This is a large-scale literature review on the last 5 years or so on the literature on melanoma screening. We were arguing and trying to urge the community to adopt deep learning for melanoma screening, and also urge the community to be more careful about the reproducibility of the results. So the first part of the paper, we don't have to worry about that anymore. It seems that the community has, at large, moved towards deep learning. The reproducibility, I think, is still an issue. And this, last but not least, this is the paper we are going to present tomorrow here at ISBI. So please, I'll be very glad if you come to watch me tomorrow at the Scheme Machine Learning session. So, moving to the competition, we participated in two tasks, the segmentation task and the classification task. For segmentation was a first for us. We didn't have any prior experience with segmentation. And to tell you the truth, this was the heroic work of Julia. We were at the time scrambling ourselves to get the results for the classification. And then Julia talked to us, okay, I'll give a try for the segmentation, let me try the segmentation. And I told her, oh, why not do that? And she carried the segmentation task practically alone. So the overall procedures were those. She used as a baseline the UNet, and used as training data basically only the challenge data. She did some attempts to use the ISIC archive data, There are a lot of data in the ISIC archive with segmentation masks available, but it didn't work very well for several reasons. We can talk about it later. And she did her experiments with a framework, a deep learning framework called Keras, using a backend called Teano, using her own computer, using her own graphics card in her own computer. And two innovations that she did is that she did she really worked on fine-tuning the data augmentation, and she did some modifications in the model, in the UNet model. So the UNet model is kind of like of an autoencoder. It's not exactly an autoencoder, but it's like an autoencoder. It's the idea that you want a network that squeezes the input, creates kind of a compact representation, and then has to reconstruct the input. The output is the same thing as the input from this compact representation. This is an autoencoder. Here we are not exactly in the same context, because the output is not the same as the input, but the output is something with the same size as the input. The output is another image which contains the segmentation. And the novelty of the UNet, is this idea that the autoencoding part and the decoding part share some weights, they share some knowledge. I'm sorry if I make any blunders, if there are people who specialize in UNets, etc., but I'm repeating everything that Julia told me. So if I make some mistakes here, they are mine. They are not Julia's. Here she did some work in also fine-tuning those boxes. That was something that she also attempted. So for this task, we had some hits and some misses. We couldn't really, things that I say didn't work out. Be careful with that, because we didn't have time to really validate the ideas that didn't work out. But the most disappointing thing that didn't work out, I think, was the use of extra data. And maybe it's because the way the masks were created in the ISIC archive, it's not exactly the same as in the challenge. It's not exactly as careful as in the challenge. This is something that I'm curious to know about from the organizers. Or maybe it's just because we didn't train for long enough. So those are the results that we got. Our validation score were about 79%, and we got a final test score about 75%. And our source code is already available. You can download it right now if you want. And we really want to try to make more samples work for this task. We believe that this pitfall that larger data training sets didn't work, that makes absolutely no sense. We have to try to find out how to make that work. And another thing that we want to do is to try to do a joint model of segmentation classification. We believe that would be a very good idea. So, moving on for lesion classification, this was a task we were much more comfortable with. This is the task, this is the model we have been working since 2014. And we had a basic strategy, and the strategy was get lots of data, get lots of computational power, and get a very deep model. So I think that this is the basic equation of machine learning in 2016, 2017. This is what makes things work nowadays. So starting with data, those are all the data sources we could grab. We were very worried because of that famous Nature paper that was published recently that mentioned 120,000 images, and we were kind of desperate to find as many images as we could to be at least in the ballpark of competitiveness, but we are worrying about also, we wanted all data to be public, all data to be at some level available to other researchers. So those were the sources we could find that anyone can, in principle, use. There are some issues with the data that are interesting to discuss. I'll not go in detail through this, but in summary, melanoma gave us a surprise. The model for keratosis wanted as much data as possible, but the model for melanoma was finicky with the data, and less data worked better for melanoma, and we are not sure still why this was true. For computation, this for us in Brazil is kind of the bottleneck. Those things are extremely expensive in Brazil, so securing enough GPUs was a problem. We had help from the University of Paris. We're very grateful to them. And then we have to choose the model to find the right model. Those are all models from TensorFlow, which are available pre-trained for ImageNet. That was a must because we didn't want to retrain ImageNet. That takes literally weeks. So we took the ones that we thought had the best compromise between being fitting in our GPU memories and having good performance on ImageNet, because from previous experience, we know that a good performance on the source task correlates with a good performance in the target task in transfer learning. So just so you take a look, this is not ResNet 101, this is ResNet 34 on the top. So ResNet 101 has almost 3 times more layers. On the bottom is a network which is already larger than the largest network we have used previously. So you see, there is really an inflation of the number of layers we are using deep learning nowadays. I found absolutely irresistible to show you this little cartoon. Maybe you have seen it. It's a cartoon that appeared in the Reddits and the social networks for machine learning in early 2016. And I found it particularly funny because I come from the statistical learning ethos. So this idea that us in the statistical learning are trying to do very, very complex, very well-founded things, and the deep learners can run over us simply stacking more layers. This kind of pain, I lived it personally. And then we have Inception, which is the other model we used. And Inception is more sophisticated than ResNet in terms of it's not just stacking more layers, but it's also a very, very deep network. So we elected a certain number of questions we wanted to ask from the beginning. So even before the competition started, we did a kind of an experimental plan with which questions we wanted to answer. There were a few more questions, maybe 3 or 4 more questions. I haven't listed that here because we didn't have even time to touch, but we were able to answer most of them. Either yes, it worked, either no, it didn't work. And those are basically the hits and misses for the classification task. I think that the 2 biggest hits, in my opinion, is that you have to use more data and deeper models. Deeper models per se didn't have a lot of impact, but deeper models with more data had a lot of impact. Data augmentation was critical. We did lots of data augmentation everywhere, and that was very important. Using normalization and using meta models was a last-minute surprise that boosted the results. The biggest disappointment, in my opinion, was image resolution. We are kind of counting on that using high-resolution images would boost the results. We didn't explore this idea to the fullest, but our experiments really didn't show any improvement. So this is a summary of not everything that we tested, but around 50% of the things that we tested. There is one graph for each task, and this graph plots our internal validations in contrast to the official validations we got in the website, in the challenge website. And what we did in the end, and those big symbols show, those are the models that we chose to compose the final ensemble, the final meta model. And here are those 7 models. So this picture summarizes what were those meta models. There are 3 and only 3 basic deep models. And then with different types of pooling in test augmentation, this is something we found to be very important. Not only training data augmentation, but also test data augmentation. And then using different kinds of final SVM decision layers, we get to a final of 7 basic models. And then we compose those 7 models in a stacked final SVM decision layer. And here again, we do an aggressive data augmentation with the stacked layer, sampling from different variations from the models. We did that because we found, to our despair, there is a lot of random fluctuations, just random fluctuations. You run the prediction, you get an AUC. You run the prediction again, you just hit enter again, and you get an AUC that's 1% higher, 1% lower, just because of random fluctuations. So this was our attempt to stabilize a little bit those numbers. So this is the final results for the classifications. This is the result we got in the official data sets. And this is the source code link, which is not available now, but hopefully will be available tonight. Tonight, maybe at 4 o'clock in the morning, I promise it will be available. So take note of the link that the source code will be available. So some open questions that we have, and I think the most critical is, why do performances drop so much from our internal validation? When you go from our internal validation procedures to the official validation procedures, the performances drop already a lot. And then when you move from the official validation to the official test, the performances drop further a lot. What's happening here? Are we overfitting? Or are worse than that, are we contaminating? Are we cross-contaminating test and training data? And we can do that cross-contamination through the human. If the human is doing hyperparameter optimization on the test set, this is a contamination between the test and the training set, because you are not supposed to learn the things in the test set. So this is something that we really have to discuss, because the performances that will happen in the hospital or in the clinics are the non-contaminated, non-overfit performances. And the only big questions that we have is image data really enough for melanoma? We are worried about that because really, in this year, we had a lot of competitors, a lot of people in the challenge, who kind of used the best state of art in computer vision. And still, the best AUC for melanoma was around 87%. This is much different than what happened for diabetic retinopathy, in the challenge for diabetic retinopathy that happened earlier this year or last year, in which the best AUC was 98%. So maybe there is missing evidence that is not on the image, that we cannot move further without those missing evidence. And some issues that I think we should consider is, even for that diabetic retinopathy challenge, which from my point of view, the machine learning part of that is over, we have already really high AUC, why those systems are not deployed yet? Why nobody is using them? So I really wanted to discuss about those things. How can we make those things useful? So I think I call that the hard, soft issues. So sorry for taking so much time. Thank you very much. If you have any questions.